Welcome back, Marauders. This is video 16.2, Bronsted-Lowry Acids and Bases. So in this video, we'll look at the definition of a Bronsted-Lowry acid and base and how to identify them in an equation. So first of all, the Bronsted-Lowry definition of acids and bases is about the transfer of protons. So an acid is a proton donor. Protons are just hydrogen ions. So if you think about hydrogen, hydrogen has one proton, 0 neutrons, and 1 electron. And then when it becomes a hydrogen ion with a +1 charge, it loses that 1 electron, so it still has 1 proton, does not have any neutrons, and now it does not have any electrons. So a hydrogen ion is just 1 proton, so we use those two terms kind of interchangeably. So anyways, in the Bronsted-Lowry definition, we're looking at the transfer of protons, or hydrogen ions. So the acid is the one that donates the proton, and the base is the one that accepts the proton. They always come in pairs, because if you have one thing losing the proton, something else has to be gaining it. It's not just going to disappear or appear. So one example is HF, hydrofluoric acid. It's an example of an acid. And when it dissolves in water, it gives its proton to water. So what happens when HF reacts with water is that the proton will be transferred from HF over here to the water. So we're transferring a proton. And so the result is going to be that you have the fluoride ion left by itself. And then you're going to have water gains another hydrogen. So it's H3O, and it has a +1 charge. Okay, this is called the hydronium ion. So H3O plus is called the hydronium ion. We'll see that quite a bit. So in identifying what's the acid and what's the base, if you see an equation like this and you see that, okay, the HF has lost the proton, lost a hydrogen, it went from this to this, then you can identify it as the acid. And then hydrogen is the thing that's picking, or water is the thing that's picking up the hydrogen ions. That's your base. Okay, so acid, donor, base is the acceptor of the proton. Over on this side, we also have conjugates. So we're going to see that these reactions can run in both directions. So the reactants can become products. Products can turn around and become back into the reactants. So imagine it going in this direction. You have hydrogens over here that would have to be lost from the hydronium ion and come back to the fluoride in order for it to become like the products, or like the reactants. Okay? So if the hydronium ion is the thing that's going to lose the hydrogen, then it's your conjugate acid. And then since the fluoride ion is gaining the hydrogen, it's your conjugate base. So the conjugates are just the things on the product side. And imagine if the reaction is running in the reverse direction, which thing is going to have to donate the proton and which thing is going to have to accept the proton. We'll look at one more example. So ammonia, NH3, is an example of a base, according to the Bronsted-Lowry definition. And that is because when it dissolves in water, it accepts a proton from water. So here, this is a base, so it's going to take a proton away from water. So what is that going to make? Okay, so NH3 gaining a hydrogen, NH4, and that hydrogen has a +1 charge, so it'll make ammonium ion, NH4 with a plus charge. And then if water loses a hydrogen, it'll become OH minus, which is hydroxide. So we're going to be dealing a lot with hydronium and hydroxide ions in this chapter as we deal with acids and bases. So we have our, in this case, water acting as an acid, because it's the thing that's donating the proton. And then ammonia is acting as your base, because it's the thing that accepts the proton. And then if we imagine this reaction running in reverse, if these products go back and become reactants again, we can see what's going to be gaining and losing the proton. So for NH4 plus to go back to being NH3, it has to lose 1 proton, lose 1 hydrogen ion. So this is your conjugate acid. And then hydroxide is your conjugate base, because it needs to gain 1 proton to go back to becoming water. One thing to notice here is that water in this equation was acting as an acid, and in this equation was acting as a base. So that's one of water's unique properties, is that it can act as an acid or a base. It can accept a proton or donate a proton depending upon what it's mixed with.